Here's the second part of Lecture 5, in which we further develop the second law of thermodynamics. In the first part of Lecture 5, we talked about Carnot cycles and Carnot engines, and let's just summarize briefly what we found there. Ignore that. Okay. So what we found was that the efficiency of a Carnot engine is 1 minus the temperature of the low temperature reservoir divided by the temperature of the high temperature reservoir. And this placed a fundamental limit on the efficiency of a perfect engine. The perfect engine means that each process in the cycle of the Carnot engine is reversible and the engine itself is frictionless. So this is the maximum efficiency of a heat engine, or the Carnot engine, which means that we were using reversible processes and we have frictionless pistons. The only way you can get an efficiency of 1 here is to have 0 as your low temperature reservoir, absolute 0 Kelvin, or have an infinitely high temperature for the high temperature reservoir. Both those cases will give 0 here, so you can get an efficiency of 1. But you find experimentally that E is always less than 1. That's experimental finding. Again, it's called the second law of thermodynamics because it's a law. It can't be proved from some more fundamental principles. It's just a generalization of everyday experience. So what we find is that the efficiency of an engine has to be less than 1, meaning you can never get a reservoir with absolute 0 Kelvin. Okay, so key points here is that we're using reversible. Okay. Let's further say that, just summarizing the previous lecture, that we had, for instance, heat transferred in from the high temperature reservoir divided by that temperature plus the heat transferred out of the engine divided by the low temperature reservoir, that it was equal to 0. Which implies that some function called Q over T is a state function. Okay. Why is that? Well, remember the Carnot cycle. You go from some initial state through some various intermediate states, but you end up back at the same initial state. So that means that if you go through that cycle and get 0, some quantity that you're adding up over that cycle, that's equal to 0. Maybe that quantity is a state function. In fact, that's what we're going to do. We're going to, well, before we go there, let's say from our discussion of the Carnot engine and Carnot cycle, one statement that we can say about the second law of thermodynamics, this is one point of, or one way of saying it, it is impossible to completely convert heat into work in an engine. Some heat will always have to be taken out in the cycle to a low temperature reservoir. All right, so that's, again, it's a law, it's our sort of a generalization of what we find in everyday experience. So we can never really convert all the heat into work in an engine. Okay, now let's define that state function Q over T as entropy. So we'll use the symbol S for entropy. I'll just rewrite that here. So ds we're going to define as dq reversible, there's reversal, that's important, over temperature. Why reversible? Well, we're sort of generalizing from the Carnot cycle, and that had reversible processes, reversible steps in it. Okay, where is it? There it is. Okay, so the heat transferred in a reversible process divided by the temperature is equal to what we're going to define as entropy, and given the symbol capital S. entropy. Well, let's integrate this ds, the integral there. That'll be the integral of dq reversible over t. And this is a state function, so this will just be initial minus final, delta S. If we integrate this, let's assume temperature is constant. So here we'll just have Q reversible, the total heat transferred in the reversible process to or from the system, divided by temperature, where here we're assuming constant temperature. All right. So that's where this comes from. Let's look at this particular expression here, which I'll reproduce here. So the integral, and if you put a circle in the integral sign, what that circle means is a closed path. So you're integrating from one point through some path and back to the same point. So if we integrate ds, s is a state function, so this would be equal to 0 because entropy is a state function. So you start from some place, go some path, end up at the same place you started from, ds is equal to 0. And this means also equal to 0 is the path integral, a closed path integral of dq reversible over t. All right, so that's some introduction to the entropy, and we'll develop that a little further. Now we're going to make the distinction that the Carnot engine and how we defined entropy was for reversible processes. But if you look at real engines, they're not reversible. In other words, to go through some cycle, it'll take some finite time for a real engine. You would have to take an infinite time for a reversible engine. So a real engine is not reversible. So when I want to make the association as irreversible processes, correspond to real processes, things, engines, and cycles you can go through in everyday life. Okay, now with that, let's consider this system. Here's state 1, and here's state 2. Let's take the system from state 1 to state 2 by a reversible pathway, and then let's go back from state 2 to state 1 by some irreversible process. Okay, now let's look at the say the change in internal energy delta U. That will be equal to 0 because you're ending up where you started from. U is a state function, and that will be the sum of this process, the reversible delta U for the reversible process, plus this delta U for the irreversible process. Let's rewrite that as Q reversible. Let's actually do the infinitesimal here. dq reversible plus dw reversible. That's what that is from the first law of thermodynamics. Let's do the same thing for the irreversible pathway. So this would be dq irreversible plus dw irreversible. Now we know from everyday experience, or from our Carnot engine or PV expansion and so on, I want to make the general statement that dW irreversible, the amount of work you can get out from an irreversible process, is always less than dW for a reversible process. In other words, the most amount of work you can get out is by going through a reversible process. Any work you get out from an irreversible process is less than that. Or in other words, let me just make this assumption, or make this idea that irreversible corresponds to real. So any work you can get out from a real process is always less than the work you can get out from that ideal process, the reversible process. Now if that's the case, this implies that the heat transferred in a irreversible process will be always greater than the heat transferred in a reversible process. Okay, so we know that this is less than that. So in order to get this thing to balance out, the real process will have to be, the Q irreversible or real will have to be greater than the ideal. Okay, so what does that mean? Let me check my notes here. Okay, so I think we're down to here. I hope I convinced you that. If not, take your questions to Wednesday's lecture or Wednesday evening lecture. Now let's consider an isolated system. Let's consider, in fact, the universe. So this is universe, which we're going to assume is isolated. In other words, there are no other universes around here which can exchange energy with our universe. All right, big assumption. If it's isolated, can't change energy, then dq has to you cannot change dq. dq has to equal 0. So dq reversible has to equal 0. What does that mean? Well, the ds, which we said was defined as dq reversible over t, that also has to equal 0. So that for an isolated system like the universe, this implies that ds reversible, we'll put reversible here, has to equal 0 for an isolated system. All right. Now, we said that dq irreversible is greater than dq reversible, so that dq irreversible over t is greater than dq reversible over t, and that is equal to 0. So this implies that dq irreversible over t is greater than 0 for an isolated system. Or in other words, if we just go down here, this implies that delta S, or ds, is greater than 0 for real processes in an isolated system. So if we now draw our universe as a process occurs, in other words, as time goes on, ds will always be greater than 0 for a real process, for an irreversible process. Now, let's take our universe and divide it into a system and surroundings. So here's our system, and here's our surroundings. And we know that the sum of system and surroundings, ds, which is equal to ds of the system plus ds of the surroundings, that has to be greater than 0 for a real process. Okay. And let's go back. So another statement of the second law of thermodynamics is that ds is equal to 0 for reversible, ds is greater than 0 for irreversible, and again, this is for isolated systems. One way to actually also say that is ds is greater than or equal to 0, where equal is associated with reversible processes and greater than is associated with irreversible processes. This is one statement of the second law of thermodynamics. Entropy of the universe is increasing, or entropy of an isolated system is always increasing. Now note that we just said that ds of the system plus ds of the surroundings If it's not an isolated system, but the total, of course, that's the universe, has to be just greater than 0 for real processes. This does not necessarily mean that ds of the system always has to be greater than 0. Does not mean. In fact, what this means in general is that the system plus surroundings has to be greater than 0. Now, if the system is isolated, for instance the universe, then the entropy change of the system has to be 0. But in general, I'll just make that point, in general, the second law does not mean that the entropy of the system has to increase with time. All right, let's look at an example of that. Let's look at our bodies. So initially our bodies start as a single cell. All right, and let's take, this is our body, and that will have a certain amount of entropy. As we grow, now we've grown arms and legs and all sorts of things. So as time goes on, we're now here, and now we have a complete system here. It would appear that the entropy of our bodies is decreasing with time. So entropy, so what are we doing? We're pumping out heat, we're maintaining our system. So does the entropy of our body decrease with time? Well, the answer is yes, it does, but that doesn't violate the second law of thermodynamics, because what is happening is here's our system, this is our body, and what we're doing is we're pumping out entropy out here, so we're decreasing our entropy, but we're increasing the entropy of the surroundings even more. So the entropy change of our body plus the entropy change of our surroundings, like the air, the world, and so on, has to be greater than 0. So if this is less than 0, this has to be greater than 0, and it also has to be greater than 0 in absolute magnitude more than the entropy we're pumping out of our body. So we're creating additional entropy in the universe, our surroundings. In fact, one might argue that that's a definition of life. In fact, that's an argument that Schrödinger, who we'll talk about in the second part of the course in quantum mechanics, made in the late 1940s. That life itself is the ability of a system to pump out entropy to decrease its entropy. Because when we're dead, well, we're dead, and our body no longer can fight against the second law of thermodynamics. Okay, so that's that. Where are we here? Here we go. So this is the second law of thermodynamics. The entropy of the universe is increasing. The entropy change of a system and surroundings increases with time. The second law of thermodynamics. That's it. Hope you enjoyed this.